Okay.
¿Empezamos? Adelante, por favor.
Okay, so I'm very happy that today we have Alicia. Also, the introduction is in English. And well, she studied in Spain at the Universidad Complutense de Madrid. And then she also worked at the European Space Astronomy Center, again, near Madrid. And well, she did her PhD in Amsterdam, where actually I met her. And she worked with Rooney Binance, and there is where she worked on X-ray binaries, and especially the BEE X-ray binaries, where she studied in detail the outbursts and the outburst evolution, and in particular the low luminosity states, where some accretion is going on, and so studying the implications, for example, of this on the accretion flows. And actually on this is where I also worked a little bit with her, and that was an experience which I really remember very fondly. And she also worked a little bit on cooling of neutron stars as well. And now, as we said before, she's now at Northwestern University in Chicago, very prestigious, and she's a postdoctoral research associate there with Wen Fai Feng. And now she's working more on gamma ray bursts, and maybe that's how some of you may have known her. She indeed appears in many GCNs and recent papers. So another thing about Alicia, which is I think is very important, and I mean requires dedication and efforts, she's also active in promoting the role of women in science and the accessibility of science to science. So I'm very happy that she's here, and as I said, she's an expert on X-ray transients, and I'm super curious to hear what she's going to tell us today. So, Alicia.
Thank you, Yuri. It's very nice to see you again, by the way. We'll talk later on. So, yeah, okay. Thank you for the introduction. Well, as Yuri said, I'm a postdoctoral researcher here in Northwestern University, but today I'm going to talk a little bit about my research, the one that I have been developing here in the USA, but also what I have been doing with my collaborators there in the Netherlands about the X-ray transients. And even though that is true that now most of my time goes in transients, especially in short GRBs, I still work on these X-ray transients because I really enjoy to work on binaries. So today I'm going to talk a little bit about these X-ray snapshots of life and death of neutron stars in binaries. But before anything, if my computer wants, okay, I would like to introduce why X-rays. And the fact is that the X-rays are a powerful tool that help us to disentangle what we can't see with our naked eye. And it has different applications in our daily life. So as you can see here, the poor Mr. Frog is having bad news about his health state. But in X-rays, in astrophysics, sorry, X-ray astronomy is a very versatile field since it allows us to study the most fundamental physical processes behind the hot and energetic universe. And it also allows us to get some data that we can access from our ground-based telescopes and facilities. And also it allows us to perform different studies at different time scales from a very fast events, sorry for the sound, very fast events in the universe, like that goes from seconds and from milliseconds to seconds, to more slower regimes that goes from days to months. So I put as an example here as the Crab Nebula in different wavelengths. And as you can see, X-rays here, it allows us to get a more insight view of what is happening inside of the nebula with the neutron star, the accretion disk, or the plasma around the jets. So they are very interesting. So once upon a time, there was like a high mass star binary. Then we had the most massive star evolved and transferred the material to the companion. And then this primary goes through this supernova explosion, forming a neutron star or a black hole. And then both of these objects live happily during some time, forming this binary while the secondary evolves. And when it evolves, we have this high mass extra binary, whether the neutron star or the black hole are linked in an orbit with this secondary massive companion. And at some point, this massive companion also evolves. It undergoes through a supernova explosion. We get again a neutron star or a black hole. And at the end of the life of this binary, we get or either neutron star binaries, black hole, or neutron star black holes. And after some time, a long time, this binary ends its life as a compact object merger, where we can have multi-messenger information with a gravitational wave emission, and then in multi-wavelength like a GRB, from X-rays to radio, from the synchrotron emission of these GRBs. So I'm mainly focused my studies in high mass X-ray binaries, and these are now in these last 2 years in GRBs and mergers of the neutron star binaries. But now I want to talk firstly of what is happening with these high mass X-ray binaries, and in particular, as Yuri said, what happens in BX-ray transients. So what is a BX-ray transient? Everyone can ask, of course. This is a binary where a highly magnetized neutron star with magnetic fields close to 10 to the 12, 10 to the 13 Gauss orbits its companion star, which is a BE type star. And these BE type stars are very particular because they are massive. They rotate very fast and spools material. And this material gets stuck in a circumstellar disk in the equatorial plane. So from now on, I will call it the accretion disk. But be aware that the accretion disk and accretion disk are different things, okay? So every time that this neutron star passes through this accretion disk, accretes material. But these systems, they can show 2 types of outbursts. The first one is linked to the path of the neutron star through the periastron, where it accretes the material from this circumstellar disk. So as you can see here, here in this light curve, we have the path intensity in the y-axis and the time in the x-axis. And the vertical lines show you the periastron passage of the orbit. So every time that the neutron star goes through this periastron, it shows an outburst and it accretes matter. So the luminosity of these events are around 10 to the 36, 10 to the 37 ergs per second. But on the other hand, we have—
Sorry, Alicia.
Yeah.
So how is that decretion disk formed? Like, why don't we have a spherical wind surrounding the BE star? Why is there that specific disk?
Yeah. So far, what I know from these BE stars is that there are not. It's like not these wind-fed binaries, where they have very strong winds and then they spool that towards the neutron star. In this case, the material, it gets stuck to this kind of circumstellar equatorial disk. And the winds, people haven't seen or detected these winds for BX-ray transients. So far, this is what I know from these stars.
Okay. Thanks.
Yeah, because in the other ones, the wind fed, you can see the winds, and then it engulfs the neutron star, and the accretion is different. Yeah. So for type 2 outbursts, as you can see here, they are much more brighter than type 1, and they can last more than several orbital periods, and the luminosity is so high that sometimes it overcomes the neutron. Like the Eddington limit for neutron stars. But the point is that having this type 1 outburst doesn't imply that we don't have type 1, because after this period, as you can see here for this system, we see this type 1 outburst again. So we have a lot of information in X-rays during accretion, since these events are very bright. But I want to complicate myself, and then I was asking myself, okay, what is happening when we don't see this activity in these systems? And what are the physical processes behind this low X-ray luminosity period? And especially what is happening to the neutron star when it's not close to the companion star and it's close to this apastron, which is the farthest point of the orbit of the binary. So some of the questions that we can have is like, for example, like what kind of physical scenarios are behind this low X-ray luminosity? Do all these systems behave in the same manner? For example, like if these B-X-ray transients behave similar to the low magnetic field neutron star binaries, which are mainly the ones that are low mass X-ray binaries. And what we find is that the neutron star period and the magnetic field strength are key components for answering these questions. So what are the physical processes that we can find out of the outburst regime? Well, we can find what we call propeller regime and low level accretion. So how does this low level accretion happens under these strongly magnetized fields for the neutron stars? So as you can see in this video, during the outburst, the accretion rate is so high that the matter overcomes the centrifugal barrier created by the combination of the neutron star spin and the strength of the magnetic field. And in this way, the matter is accreted on the magnetic poles of the neutron star. However, once the accretion rate starts to decrease, the effect of the centrifugal barrier is more noticeable. And at one point, the matter starts to be propelled away. So as you can see, maybe at some point here, there will be some emission, some matter that is expelled from the system, from the neutron star. So in this regime is what we call propeller regime. And what we know is that the accretion of matter on the neutron star surface is centrifugally inhibited. The question here is that and I will show you later on, is that we have seen some accretion events even though being in this propeller regime. So the question is like, how is it possible if in theory the magnetic field and the spin of the neutron star, they are stopping this matter to reach the surface of the neutron star. So what we see in X-rays is like if we plot the luminosity in X-rays and versus time, we see the rise of the outburst. And then when it starts to decay, suddenly there is a very sudden change in the decay or the slope of this light curve. This is an indication that the system entered the propeller regime. And this decay happens like in super short times, like 5-10 days, whereas in other outbursts, like normal outbursts, it can take more than 1 month. And now the question is like, what happens here when the system finishes the outburst? And here it enters the heating cooling process that maybe Danny and Yuri are familiar with. So for low magnetic field neutron stars, this means 10 to the 9 Gauss. What we have is that before the accretion, the crust and the core of the neutron star are in thermal equilibrium. And then once that the accretion starts, the luminosity goes up. So what happens is that matter is deposited on the surface of the neutron star at this compress the inner layers of the crust of the compact object, and this makes that certain reactions being triggered there, and then the energy they are highly energetic, so heat is released and the crust start to be heated up, and then the thermal equilibrium between core and crust is broken. So once that the accretion is stopped, the crust and the core try to tend to restore this thermal equilibrium. And then what happens is that a release of this excess of energy that is in the crust try to escape from the surface as cooling emission, which is thermal emission, and towards the core. And what we see in X-rays is basically this thermal emission from the cooling. So if we go and take our observations in X-rays and take spectral information, what we see is that there is a temporal evolution of the temperature of the surface of the neutron star, decaying in time. So what happened then when we have high magnetic fields in these not these low magnetic fields neutron stars, but in B X-ray transients, and how this magnetic field affects the heating cooling scenario in the neutron star crust. So it can happen that, for example, like reactions happen, like they occur close to the core, and then the magnetic, the magnetic field lines are confining these reactions close to the core, and therefore the neutron star outer layers of the crust are cooler, or maybe these reactions happen closer to the outer layers, but the core is cooler, or the structure of this magnetic field is random or a little bit kind of, I don't want to say crazy because it's a bad word, but like unusual, and then things get complicated. So this is something that Rudy Binance and Danny were already working on. And then the thing is that Danny and his group are working this, upgrading his code, the NS cool, to include the magnetic field, that I think you already did it. And then the idea is to also play with the strength of this magnetic field and the structure inside the crust, and compare these models towards the observations that we get in X-rays. So these are the two scenarios that we can see, but we have a third scenario, which is called disk scenario. Is what we call accretion from a non-ionized disk. So this scenario, it takes place for neutron stars that spin very slow. For me, neutron stars that spin very slow is like larger than 100 seconds. And what happens is that after outbursts, these systems don't enter the propeller regime, so matter is not expelled out. And since the neutron star is spinning very slow, the residual accretion disk that is there has enough time to cool down, and therefore it's not ionized. And since it's not ionized, the magnetic field don't interact with the material in that disk. So what happens is that due to the potential gravitational potential and the kinetic energy, when the accretion disk gets closer to the neutron star, the material in the disk gets ionized, and this makes that the magnetic field lines accretes this material that is ionized again to the magnetic poles of the neutron star. But the outer layers of the accretion disk, in theory, are cooler than the inside part. So how we see these things, if we plot the luminosity in X-rays and the versus time, we see that we have normally type 1 outburst, and then there is a nicely decay luminosity period, and then it shows again type 1 outburst close to the periastron. So the idea is that during these accretion events, the cold disk is replenished. So you have these normal outbursts, and then in these low luminosity states, it has this cold disk accretion. So now what I'm going to show you is that these are the not theoretical, but what is the physical processes behind these low X-ray luminosities. Now I'm going to show you the results that we got for these scenarios. What we see is that the behavior of these systems can be grouped in 3 different families, depending on the neutron star spin. So we have the fast rotating neutron stars with around less than 10 seconds, slow rotators with, I already said, more than 100 seconds, and intermediate rotators. So let's start with as fast rotating neutron stars. I'm introducing here one of the samples that we got. The system is called 4U0115. And in 2015, it showed a very nice type 2 outburst. And we monitor it with Swift Observatory. At some point when the outburst finished, we got an observation with XMM Newton. So we know, as you can see here already, there is the outburst and then suddenly a change in the decay of the outburst. We know by models are done for, by other groups that the outburst enter in the propeller regime. And then from previous observations from this system when it wasn't accreting, we know that the quiescence level is there. So as you can see here, we have, after the outburst, we have a very nice emission over the quiescence level. So the idea was like, okay, what is originating this emission? And the answer that we think of was that maybe it's due to this cooling emission from the neutron star surface. And this was also proved by our XMM Newton observation. So if we plot luminosity and temporal evolution in temperature and the radius of this emission region versus time, we see that there is a nice decay in luminosity, in temperature, and also, as you can see here, the radius of the emission region doesn't change too much. And also, this is important, if you can see, it's very small. So what is happening here is that we are seeing emission from the magnetic poles. So these emission regions are basically the magnetic poles of the neutron star. But we wanted to continue our monitoring, and then suddenly, of course, this happens because when you observe too much, you have another observation there that suddenly the luminosity goes up, temperature goes up, and in theory, this is super difficult to explain in a temporal, like in the cooling scenario. And here, Yuri was helping us to kind of try to understand what was happening there, trying to put a cooling scenario. But if we go and change and see, okay, what is happening in these three different points, and we place them in the light curve, you see that number 1 and number 3 are close to periastron. We know that type 1 is what we call a type 1 outburst. And number 3 is not as luminous as 1, but also it's not like 2. So we weren't very sure what was happening there. And so we tried to explain this thing at the beginning with a toy model that Yuri developed. But after some thoughts, we thought that this event is due to low-level accretion. And this low-level accretion is different from the 1. And as you can see here, if we have the spectra of these 3 events or 3 points, you can see nicely that the type 1 is different to, sorry, the type 1 outburst spectrum is completely well modeled by a power law, and it's different from the thermal spectrum from number 2, which is the temperature of the neutron star surface, sorry, so the magnetic poles. And number 3 is, for sure is not thermal emission, and since we don't have very good statistics, we couldn't say that is as the same as the type 1 outburst, but it has differences with the number 1. And this was also proved in 2017, because this system entered again in a type 2 outburst, and we saw similar behavior, and close to the periastrons, we see this kind of events. So the thing is that now a question to answer is like, why there must be some maybe differences in the accretion flow that makes this kind of accretion different from type 1 outbursts. Let's jump to slow rotators. Here I'm showing you this system, GEO1008. And you can see that it nicely has like type 1 outbursts in every periastron. And as I told you here, you have this nicely decaying emission that we know now that is due to this called non-ionized disk. And just to show you here, this system doesn't enter propeller regime. It's like the propeller regime is 2 times 2 orders of magnitude in luminosity fainter. And just for showing you and put this in perspective, for 4U115, the quiescence level is even lower. So this emission has to be originated by something different that is not cooling. So yeah, we have this aggression due to cold disk, and we wanted to try to prove this scenario for other system, GX3041. And as you can see here, there are type 1 outbursts, and there is like a small emission at low X-ray luminosity, and then a type 1. And then we thought, okay, maybe there is a cold disk. But for us, we didn't monitor this period of time, but we started monitoring at late times here. And you can see here that there is not any type 1 outburst. So now the question is, how is it possible that if the accretion disk is not being replenished in all these type 1 outbursts, why we have still this continuous emission there? Because in theory, this cold non-ionized disk has to be empty at some point. So these are one of the questions that I want to address in my future work, maybe next year. But what we see here is that, for example, like at late times, we monitor with Swift XRT, and you can see that like the vertical lines again are the periastron passage of the system. There is a kind of variability. And also here we obtain a new star observation together with Swift. And what we saw is that we have pulsations. So that's good because we can test that the system is kind of accreting there. And the other thing that we see is a spectral evolution. So if you compare the outburst spectrum with this cold disk phase, you see a completely different spectral shape. So this is due to emission. And here we have two components. And these two components have been explained as different emission regions in the column, in the accretion column in these magnetic field poles. We cannot explain here, we cannot say that we see the thermal emission from the neutron star surface, since as you can see here, the temperatures, the energies are very high. And normally the temperature of the surface of the neutron star peaks around lower energies. So these two components are different emission regions in this column density. And this dip here is what we call cyclotron lines. And it has been mentioned that maybe this dip is a cyclotron line that tells us about, is originated by the magnetic field of the neutron star close to the surface. And last but not least, we have these intermediate rotators. And these systems are a little bit messy for me, but I want to start also studying them. I think we don't only need the X-rays, we need consistent multi-wavelength observations of these systems. Because with X-rays, as you can see here, we in the BAT, but also in Swift XRT, we see this outburst and then a reflaring activity that is not linked to any periastron passage. There is here a period where the system doesn't show any activity. So what happened there, like the accretion disk disappear and then appears again, but it's not linked to this periastron. So what we think is maybe is due to a combined structure of the binary plane with the circumstellar disk of the companion. But for this, we need optical observations because in the optical observations, in the optical and the UV, mainly in the optical, you can see the contribution of the star and also the decretion disk, because if there is a decretion disk, there is an emission in H alpha. So maybe there we can explain that if the accretion disk, or the decretion disk is very extended and thick, maybe the neutron star is accreting from that disk, but we definitely need multi-wavelength monitoring. So this is what you can might take away from this part of the talk. So if you have any question, I can take it here, or I can continue if you want.
I do have a question.
Yeah.
So I'm not really clear. I knew at some point, I forgot what's the difference between a type 1 and a type 2 X-ray outburst. Is it only observational, or is there a physical difference from the theoretical point of view?
So so the system is, so what is behind there is accretion, but the accretion, what triggers the accretion is different. So for example, for the type 1 outbursts, what happens is that you have the companion star with the circumstellar disk, and every time the neutron star passes, like it goes through this disk and accretes matter from that. And every time that it goes out, then it stops accreting and again accretes again when it reaches the companion star. However, in the type 2 outburst, we really don't, there are models and there are some explanations for this, but what is thought is that this disk around the star must be either grob or, and also like has some inclination, and it gives more time to the neutron star to accrete more matter, so that the accretion is power during more time, and then therefore you have a brighter outburst.
So from the observational point of view, is the duration the difference between one
and
and
the brightness? They are much, yeah, they are, they reach 10 to the 38 X per second.
Okay, and the hardness, is it the same for both?
In the accretion, like the, sorry, the spectral hardness.
Yes, yes.
So in particular, like type 2 outbursts used to be harder, sorry, than type 1, but both of them are harder. Like there is accretion there, like, yes.
Okay, all right, thank you.
You're welcome. Okay.
I have another naive question. So what I don't understand is this decretion disk, like how thick is it? So when the neutron star is closed in the periastron, is the neutron star embedded, engulfed within the accretion disk, or is the neutron star, and so it accretes like wind-like, or is the neutron star larger than the accretion thick, and so the accretion is equatorial?
Yeah, so these models I saw, so there was now it's a postdoc, a student in, he was in Southampton. He was modeling this, the neutron stars going through these disks. So the disk, so the neutron star is not like it's not bigger than these disks. So it goes through these disks. Like, so you have the disk and then the neutron star is going through it. But what I didn't mention, and I should have said that, is that this is something that also the people don't know, the people that study BE stars, is that these disks are not continuous, like they don't exist continuously. They disappear, they have temporal behavior. So there are years that they appear and they are still there, and then suddenly it disappears. And they cannot explain why that thing is happening. And this happens in normal BE type stars, and also happens in BE type stars with a companion as a neutron star. So sometimes this disk is super thin. So for example, like for this system that I said that I wanted to study further because it's emitting after 4 years without showing any outburst. Some collaborators from South Africa, they show me the spectrum, and the disk is super thin and small. So how it is possible that, you know, the neutron star is even getting closer or accreting from something super thin? So there must be another thing. But in theory, if this circumstellar disk is there, the neutron star is going through it.
Vale, thank you.
I do have another question, a little bit in line with what Diego was asking. As far as I remember, B stars have this decretion disk from fast rotation, but B stars are not the only ones which can be found to be fast rotators. Is there any idea why do we see BE and not AE or OE stars and this kind of binaries around those?
That's a old question, but that goes further to my knowledge in stars. Sorry.
Okay.
But yeah, it's a good question. Yeah.
Right.
There is, I'm trying to remember from when I was studying these things, but like not be extraordinary, but when I was at university, there were also type AE stars, something like that. So the more towards the late times stars with some disks.
Yeah, I think there's a few cases with both, with O and A's, but they are not as common as B type, as far as I can remember. And there's also the BE bracket stars and other things, but they are particularly centered around B stars. So it must have to do probably with luminosity and rotation or something like that.
Yeah. Yeah.
Okay. Yeah.
Yeah. I'm sorry.
No problem. I was just curious about.
Yeah, but it's a good question. Okay. More questions? Okay. You can, if you get with more questions, we can continue later on. It's because I don't want to bore you with more of these things. So now I'm going to jump to other type of things. I'm glad that Rosa is here, by the way, because I'm going to introduce some part of my work in a GRB that she was working on as well. So yeah, now I'm going to talk a little bit about what I have been doing here during these 2 years in the GRB field. So just to give you like a little bit of a background, so the GRBs are rapid and highly energetic explosions that release gamma ray radiation, and they occur at cosmological distances, in the sky. So gamma ray bursts can be divided in 2 families normally. We have the short GRBs, which they are short duration GRBs with less than 2 seconds. They are less energetic than the long GRBs, and they normally appear in lower density environments. And now we know that the progenitors of these, some of these short GRBs have as a progenitor double neutron star mergers, and this is due to the discovery of the joint emission of the gravitational wave plus the detection of this short GRB in 1708-17. In the case of the long GRBs, they are longer duration, more than 2 seconds. They are much more energetic, and they appear to happen in higher density environments, especially because they are more located within the host galaxy. And we know that the progenitors are massive stars, so they happen due to the death of these massive stars, and they normally are related to supernova, like remnants around the position or location of this long GRB. So, for example, let's go and talk a little bit more about the neutron star mergers. So, when a neutron star merger happens, we detect a short GRB, and the internal engine launches like a highly collimated and relativistic outflow that is what we call jet, and this jet evolves in time, interacting with the environment. And at some point, the Lorentz factor of this jet equals the value of the inverse value of the opening angle. And then if we are observing this normally in the side of line, in the observational line, we see a jet break. So how is this translated in what we see? Is that in our light curves, if we have the flux in X-rays and versus the time, we see that it nicely decay in X-rays, and at some point there is a change in the slope of this decay, steepening, and this is what we call the time of the jet break. So inferring from these times, we can get some calculations, and thanks to broadband analysis, we get the value of the opening angle of the jet. And with these opening angles, we can get some distributions for short long GRBs, and with some calculations, we can infer the merger rates that later on we can compare with the neutron star merger rates from LIGO, or the ones that we get from some theoretical work done in the galaxy for this kind of neutron star mergers. So 1804-18A was monitored by different observatories. And now I'm going to talk about this GRB, since it was a very interesting GRB, since I will tell you a little bit more now, but in theory, its duration was more than 2 seconds, but then it's showed to be like a short GRB. So let's go and talk a little bit about the high energy information of this GRB. So this GRB was detected by Fermi and observed by Swift. So if you can see here, the Swift path duration tell us that is around 1.9 seconds, but however, Fermi put this around 2.5 seconds. This, by the way, this duration was after doing several tries in different bands with energy, trying different also binning. But this was the nicest location for the duration of this GRB. But anyway, it doesn't matter. As you can see here, the duration is around more than 2 seconds. So it was like, how is this possible that we have a short GRB, since in theory is a little bit longer. So if it is short, the long has longer duration. And if we place here the hardness versus the duration of the burst, here, as you can see, is softer than the normal short GRBs that are here in red. If it is long, then the duration is very, very short. So, and also we didn't see any kind of remnant or related to this or detection in optical observations for remnants. So how was to disentangle this thing? So if also we plot here the hardness versus time, we also have here, as you can see, 1708, 17A, and they fall kind of similarly in the same area. And if we draw the probabilities of being short and long, we can see that the probability of being short is a 60%. It's not 100%, but it still is around a little bit longer, like larger than the 50%. So we can more or less say that it's a short GRB, but still we need more information. So let's say we continue and go and talk a little bit about the X-rays of this GRB. So we got information from Swift and also observations from Chandra at late times. And as you can see here, at the beginning, we had a very nice decay, but suddenly we have like a plateau. So these plateaus are normal. Some of the GRBs show this plateauing. But if we later on, I will let you know, but what happened here is that thanks to our late time Chandra observations, you can see here that the afterglow of the GRB was nicely detected. And here you have another extra X-ray source. So, and this area is the XRT or Swift source region that was used to get the information. So it's clear that we have a contaminated source in the source region. And here you have more information. So in XRT, we have here the X-ray afterglow plus the combination of the contaminating source that you cannot resolve with the power of XRT. So what I did is to model this contaminating source and have this into account in the X-ray analysis. And as you can see here, that plateau disappeared. Then if we can go larger, we see here our late time observation with Chandra. And sadly, we don't detect any jet break, so we cannot infer any detection of opening angle, but we can infer some lower limits for the opening angles of the jet of this event. And another thing to say is that this GRB enters in the group of GRBs that have been detected at very late times. We got 37 up to 37 days. It was still detected in X-rays, and this is very, very weird because normally short GRBs, or at least this can be like a bias, by the way, but normally short GRBs are observed up to two days as longer. But it's also because we don't observe at late times these events. So as I said, it can be a bias there's a question of bias.
And is there any way to know then what that extra X-ray source may be?
This one?
Yeah, that
Yeah.
Excellent.
So it was so we had we had 3 observations with Chandra, and the source was continuously there. So my guess is that it can be a galaxy because the spectrum was quite hard.
Okay.
Alicia, and why you don't see the jet break? So
Here, well, it can be either that. It can be either that it's very collimated and it didn't go through the. We didn't see the jet break still, or maybe it's observational. We are completely out of this of the line of sight.
okay.
But I think like the most probable is, explanation is like we are not in the the jet is very collimated. Sorry, it's not very collimated. I'm lying to you. Is that we are very out of the line of sight and we don't see anything there.
But you see the gamma rays.
Yeah, we see the combination. Sorry.
Yeah. I mean, for instance, in the case of the 17,
yeah.
you saw. I mean, we saw just low flux, no?
Yeah.
Well, in this case, it was a regular GRB, right?
17 or 17?
No, this one.
This one?
In this one was a regular one, or it was soft?
It was quite soft here.
Okay.
Yeah, here is this one.
Okay.
So yeah, it was quite soft if you compare with the family of short GRBs.
But if you compare to the long GRBs, it's kind of average, right?
Yeah.
Okay.
Yeah. Okay. So yeah. So, but and then yeah, because this thing we couldn't say completely that is a short GRB because still you have this hardness that is similar to long GRBs. But we did extra analysis here, and we compare the rest frame time of this, the rest frame time, the X-ray luminosity versus the rest frame time of this GRB, and with other short GRBs and the family of long GRBs. And as you can see here, you have the long family, the long GRBs family, and here the short GRB family. And it falls nicely within the family of short GRBs. So we select from the Swift GRBs, those with known redshifts. So we have 350 long GRBs and 37 short GRBs. And then we introduce some of the GRBs, short GRBs that have lead time information with XMM, Newton, and Chandra. So there are, you can see this area of the diagram is not very populated because it's also expensive to observe some systems, some events with XMM and Chandra. So what we did is to place this GRB in 2 different redshifts, and I will talk a little bit more further about this redshift selection. But if we do like 2 temporal slices and compare the position of our GRB with towards the long and short GRB, at early times, you can see that independently of the 2 redshift positions, it falls within the end of the short GRB family distribution, and at the beginning of the faintest, let's say, long GRB distribution. If we go to later times, we see here that it could be either short GRBs or long GRBs. It is true that it's in the peak of the long GRBs, but I'm saying here that we have this observational bias that short GRBs are not observed very often at late times. So we have to take these things into account. And this is something that we are pushing to populate short GRBs in this area. because definitely there are some of them that are observable. And finally, just to grab together all the information, this was the latest proof that this GRB could be short, is that if we plot the prompt spectral information of the prompt emission of this GRB, and we have the energy peak and the isotropic energy, and we plot the family of short GRBs and long GRBs, we see that this GRB falls nicely in the trend for short GRBs. So this was kind of extra point to underline that this GRB could be short and was potentially short. So let's go now and talk a little bit about the other potential, like multi-wavelength information that we have from this GRB. So 1804-18A was observed by Ukir, MMT, and Gemini. So as you can see here, we follow up it, and we have a nice detection of the afterglow of the event. And then at late times, we got a kind of a slightly detection of a potential host galaxy. So we could infer the redshift of this host galaxy in between 1 and 2.5. So this is a nice wrap up, because we could, there are not often GRBs with detected host galaxies. And these values are in agreement also with the values that I think Rosa, please correct me if I'm wrong, but what she put in her paper. So in the paper of Rosa, they say that they detected the first time a reverse shock in optical for a short GRB and at so early time. So it's very nice and incredible. And then with our latest spectral analysis of the, synchrotron analysis and multi-wavelength, we confirm that there is a reverse shock and a forward shock with the afterglow. And as you can see, nor for any of these light curves, in different wavelengths, we detect a jet break. So we can say that we get a upper limit for this, a lower limit for the opening angle. So if you can see here, we know now that thanks to the broadband analysis and isotropic energy and density, chat, I'm seeing, I cannot see my chat now. Yeah, thank you, Rosa. We can see that at least depending on the, I'm sorry, I had to update this value, it was 205. We can say that at least the opening angle of this system is above the 5 degrees, is around 9 and 10 degrees. So just to wrap up, we know that, based on the traditional classification of GRBs, based on the duration and hardness and the amateur relation, we can say that 1804-18 is most likely short GRB and potential and most likely, and I think it's a short GRB. The only thing is that we need to redefine maybe what is a short GRB and long GRB and study these kind of cases that are in the limit to see if they are short or long. 1804-18A is the first short GRB with a reverse shock detected in the optical band and is self-consistent with the reverse shock model parameters. We also find a faint host galaxy in the optical. And thank you to the X-ray and optical afterglow studies, we can constrain the lower limit of the jet opening angle between 9 and 14 degrees. So now the story is that we need to populate this area here for either getting a better constraint of lower limits for short GRBs or detect at late times these jet breaks and get more opening angles to get a distribution of these opening angles and therefore to calculate the merger rate for neutron star binaries. So with all of this, I leave here my second takeaway message. And I thank you very much for your time, everyone. And then I'm open to more questions.
Felipe?
Sí. ¿Alguien tiene preguntas?
Bueno, yo el comentario de que no había leído en detalle tu paper, si lo había visto, entonces, pues me gustó mucho, ¿no? Que claramente ustedes se enfocaron en la parte complementaria y pues yo no tenía observaciones en X, ¿no? Entonces, claramente es como reforzar un poquito el punto que nosotros habíamos publicado. Entonces, digo, nada más así como hacer énfasis, porque casi todo el mundo es teórico, ¿no? Entonces, hacer énfasis en que claramente sin la distancia no se puede hacer mucho, ¿no? Y este punto que siempre remarcamos de la clasificación solamente con el T90 no es confiable al 100%, ¿no? Y este es un claro ejemplo de ello. Y cómo te cambian los escenarios solamente por, tanto por la distancia como por la duración, ¿no? Entonces, nada más era ese comentario. Está muy bonito tu paper.
Gracias, Rosa, y gracias por el trabajo. Además, o sea, te voy a ser sincera, fue mi primer artículo acerca de GRBs. Me abrió como un nuevo universo, por así decirlo. Y fue, claro, yo no sabía cómo enfocar las cosas, pero gracias a tu paper, y además estuve súper, o sea, me puso muy contenta que al final tus resultados y los resultados a los que llamamos nosotros se complementaban. O sea que perfecto.
No, y además salieron estos otros dos papers, ¿no? Que ya no sé si eran cortos, pero luego analizando a Matt y el hardness resulta ser largos o viceversa, no me acuerdo. No salió ahí en Nature, ¿no? De Bing Sang y había otro más, creo.
Sí, ese paper, sí. Y de hecho, yo creo que, a ver, sí que, porque esto es otra cosa, yo tampoco soy una experta en la gamma ray emission, porque colaboramos con algunas personas en Fermi y demás, pero que siempre me dicen, tienes que tener cuidado con el análisis espectral de estas cosas, bla, bla, bla. Pero si tú realmente pones toda la información que hay, puede ser eso, una herramienta más para la clasificación de algunos sistemas que, pues, o sea, de algunos eventos que se escapan un poquito a lo normal.
Creo que nadie... Creo
También
que
solo un comentario, que también hay, recientemente han salido papers donde hacen cosas de machine learning para clasificar GRBs, ¿no? Entonces,
sí.
¿te referías a eso ahorita cuando decías que lo de gamma se puede usar, etcétera?
Sí, también ese van, no me acuerdo del nombre del autor, o sea, creo que es holandés, es holandés, Van Aerten.
Van Aerten.
Henrik Van Aerten.
Sí, esos estudios, sí.
yo creo que más nadie tiene preguntas porque no hay manitas. Entonces, muchas gracias por la presentación, estaba muy buena. Y voy